All right, let's peel back the curtain on something that runs pretty much everything around you, but you almost never see it. We're going to dive into the unseen brains of our world, industrial control systems.
So think about it for a second. Your car, the electricity in your house, even the traffic lights on your way to work. There's a hidden intelligence making it all happen. But, before we had modern computers, the solution, well, it was anything but intelligent. Not that long ago, controlling a machine meant using what they called hardwired logic relays. Just picture a gigantic wall, completely covered in a tangled mess of wires and switches. It was crazy complex, super expensive, and if you needed to change just one little thing in the process, oh, it was an absolute nightmare to track down the right wires and fix it. Yeah, so that system obviously wasn't going to last. Industry needed something better, right? Something smarter, way more flexible. And this need sparked a huge shift, moving away from all those physical wires and into the world of programmable logic. It was no joke, a total revolution in automation. And sitting right at the heart of this revolution is this little box, the Programmable Logic Controller, or PLC for short. The best way to think of it is as a really tough industrial-grade computer. Its whole job is to run machinery. It's constantly watching for inputs, like a sensor tripping or a button getting pushed, and then, based on the program we give it, it decides which outputs to turn on, like firing up a motor. And the way a PLC is built is just brilliantly simple. You've got the CPU, that's the brain of the whole operation. It's connected to input modules that get all the signals from the real world, and output modules that send out all the commands to the equipment. And of course, a tough power supply to keep it all running. This modular design is exactly what makes it so powerful and versatile. So, why do PLCs totally take over the industry? Well, for one, they're incredibly flexible. If you want to change how a machine works, you just upload new code. You don't have to rewire the whole factory floor. They're cheaper, they take up way less space, and troubleshooting a problem becomes a software issue instead of a desperate hunt for one broken wire in that giant mess. Okay, so a PLC is great for running one machine. That's cool. But what about an entire power plant? Or a whole city's water system? How do you manage hundreds or even thousands of things happening all at once? Well, you need a supervisor. And this brings us to two major ways of thinking about large-scale control. First up, you've got SCADA. That stands for Supervisory Control and Data Acquisition, and it's all about watching over everything from one central spot. Then you have DCS, or Distributed Control Systems, which spreads the control out over many different locations. Let's kind of break down how they're different. A DCS is all about the process itself, using super-fast local control. It's perfect for something like a chemical plant, where all the steps have to be perfectly timed and connected. SCADA, on the other hand, is all about the data. It's built to supervise systems over huge distances, like a nationwide power grid or a gas pipeline. It's more focused on high-level monitoring than on that second-to-second control. So what SCADA really does is give a human operator this incredible bird's-eye view. From a single control room, they can see what's happening at hundreds of different sites, log all that information, get alarms if something goes wrong, and send commands out to all the PLCs and controllers out in the field. It's the central command center. So we have these powerful computers running our world, but how do we actually tell them what to do? You might be picturing lines and lines of complex code, but the most popular language is surprisingly really visual and easy to understand. It's called ladder logic. And here's the genius of it. It was designed to look just like those old-school electrical wiring diagrams that it was replacing. This made it super easy for electricians and technicians to make the jump from physically wiring things to programming them digitally. The whole language is built from a few really simple parts. You've got contacts, which are basically like switches that represent inputs, and coils, which are like the motor or the light bulb, they represent the outputs. The two vertical lines on the side are the power rails. The whole goal is to create a complete path for electricity to flow from the left rail to the right. If you do that, the output turns on. Simple as that. Let's look at a quick example. This is what we call an AND gate. For that output X to turn on, a signal has to go through input A and then through info B. If either one of those is open, the path is broken and nothing happens. It's just a series circuit. Super simple, super logical. Now compare that to an OR gate. See how the inputs are in parallel here? That means power can flow through the top path with input A, or it can take the bottom path through input B. As long as at least one of them is on, that output is going to turn on. And it's this kind of flexibility, building up from these simple blocks, that lets you create any kind of complex logic you can possibly imagine. So, we've covered the hardware and we've covered the software, but let's bring this all back home. Why does any of this actually matter to you? Well, because this entire invisible system is, quite literally, the backbone of our modern lives. You find these control systems everywhere. I mean, literally everywhere. They're running the traffic lights that get you to work, they're controlling the robot arms that built your car, they're making sure your water is clean, and they're keeping the runway lights on at the airport. They are these silent, tireless workhorses of our entire infrastructure. Really, the key takeaway here is that whole journey, from that chaotic, inflexible mess of wires to this elegant, powerful, programmable logic. That evolution right there is the hidden engine that makes the incredible complexity of our modern automated world actually possible. And that kind of leaves us with one final thought. We've seen how this tech has completely transformed manufacturing and our power grid. Now that you can see the brains behind the whole operation, what's next? What part of our world is about to be quietly reshaped by all this logic and code? Something to think about.